particles are called point-like and at the same time are non-localized.
And but this is a different story. Your point can be, so point-like doesn't mean that you have exact localization. It may be here or there or in some other place.
So you don't know where it is, but whatever it is a point.
Yeah.
Okay.
So remember, we had this huge number of scales. Let me remind that we had here TeV scale, where LHC is sitting. Then let me put here MEV, which is 6 orders of magnitude. Then it is 1 electron volt. Then it 10 to the minus 6, 10 to the minus 12, and so here we go up. This is E electron volt. Then it will be 10 to the 15 GeVs, and then 10 to the 21. So here somewhere we have Planck scale or string scale. And all our particles, it turns out, are sitting somewhere here, say from this scale to this. So it's a small island. There are many particles here, which we'll discuss. So there's another island here, which probably belongs to neutrinos. These are neutrinos. And what I would advise you, I'm doing this, I'm always keeping these scales in my head. We will discuss different particles, different masses. Produce for you this scale and put particles on this scale, because you will then see what are difference of masses and where this particle is sitting. This is very important to know the masses of particles. Actually, mass of the particle is essentially identification of a given particle. There are a few cases when you have equal masses or almost equal masses of the particles. But to some extent, saying what is the mass of the particle, I can say what is this particle. So, for instance, we have strong degeneracy between pions. We have pi 0, pi plus, pi minus. Pions with different electric charges, and they have very close masses. So here you need to specify even more. But even in this case, you can identify particle by the mass. So this is what is called high energy desert. And most of the efforts to find something new was actually focused on this range, above, say, TeV. And this is where we are looking, the LHC is looking for some new physics. People didn't worry much about this low scale desert. Of course, we have photon, I'm not indicated here, so photon has 0 mass, and we think, and gluons have 0 mass, and gravitons have 0 masses. Well, actually, the scale of something like 10 to the minus 33 electron volts can be considered as essentially physical lower bound, because this is the scale. This scale corresponds to horizon. What is horizon? Horizon is, say, in the universe, you have the surface above which you cannot get a signal because everything is propagating with velocity of light, and you still have not enough time. So it is related to lifetime of the universe. So you have 14 billion years of the universe, then multiply by velocity of light, you will get this size of horizon. And that inverse will give you this 10 to the minus 33 electron volts. Which means that if you have particle which has a smaller mass than this, you essentially will not find any manifestation of this particle in the universe. So not much sense to say this about the particles, if it is massless or not. If the mass is smaller than 10 to the minus 33, then for us it's almost just massless particle. So, what is here? Nowadays, people start to focus on this low scale, partially because LHC is not finding anything here, and we have very precise measurements of some processes, or give very strong bounds on some possible processes beyond the standard model, and this actually tells us that probably there is no new physics even here above this LHC scale. So it doesn't look that there's no smell that something is sitting here, although it is not excluded. And if you want to have some new physics above the scale, say, close to TeV, you need to satisfy many bounds which we have already on new physics, and therefore you need to kind of do some tuning to survive. For this reason, in some kind of 5 or 6 years, the paradigm of such something new changed. And now people focused, many working in this range, trying to populate to see what we can actually get here, what we can find here in this range. Partially it is related to this dark universe, so we don't know what is dark matter, what is dark energy. Maybe something is related to this dark is sitting somewhere here. So its popular topic is to explore dark sector of the universe. So I'm saying all this because eventually you will need to select your topic of future research, and so I will mention many times what a real problem these days, because you need to decide what you will do in the future. By the way, if someone wants to do some diploma thesis with me, please tell me, so that can be arranged. Okay, so this is the energy scale, and then, as I said, there are complementary scales. And complementary scales are distances, right? So, distances. And we can establish relation between these scales and the energy and momentum using uncertainty principle. So we have delta P, uncertainty in P, we know that it is h over dx, or vice versa. So delta x is h over delta p. And therefore, if h is 1, as we decided, then the distance can be measured in inverse of energies, of momentum. So energy and momentum for us is the same. 1 electron volt actually corresponds to 2 10 to the minus 5 centimeters. So 1 electron volt equals 1 over 2 10 to the minus 5 centimeters. And we will have some exercises to play with these units. Now, 1 GeV corresponds to 2 10 to the minus 14 centimeters. It's inverse of 2 10 to the minus 14. And in fact, this kind of complementarity has deep sense, deep physical sense. Again, it is already related, you see here, with uncertainty principle. Now let me give you some important scales in distance. So here I will have 10 to the minus 2 centimeters, 10 to the minus 5, 10 to the minus 8, and I put scale, inverted this scale. So this 10 to the minus 8, this 10 to the minus 11, 10 to the minus 14, 10 to the minus 17. These are distances in centimeters. So important scales are around 10 to the minus 8 here. And this is Bohr magneton. And Bohr magneton is Bohr magneton is 0.53 10 to the minus 8 centimeters. And this is typical size of the radius, and this is typical size of electromagnetic phenomena. Now the scale 10 to the minus 13 here, or more precisely 1.3 10 to the minus 13, This is inverse of mass of pi. And pi is the particle which is supposed to mediate strong interactions. And that corresponds to 1.4 10 to the minus 13 centimeters. So this is inverse of fine mass, and this is typically a radius of strong interactions. Actually, we can introduce 1 over lambda QCD, but I will specify this later. Now, the proton is somewhere sitting here. So this is inverse of mass of the proton. Another important scale is 10 to the minus 16, and somewhere here. And this is inverse of mass of the W boson. And this is typical radius of weak interactions. Well, actually, the nuclear sizes are somewhere here, right? So 10 to the minus, again, 13 centimeters. It's nuclear size. And for this, we have introduced some special units. This is 1 Feb to minus 13 centimeters. Well, that corresponds to inverse of keV, which is the energy of in atoms. And finally, remember we discussed here that LHC is checking up to scale 10 to the minus 18. This is LHC scale of checks of point light or structureless of quarks. Okay. Another complementary scale is time. And again, we can use energy units even for time, or inverse energy units. And this is related again with uncertainty principle, and we have delta T is 1 over delta energy when H is 1. So what are important physical quantities which we characterize by time? So these are rate of the processes or lifetime of particles. Now, time of the process. Which is inverse of the rate of the process. And time of the processes characterizes the strength of the interaction. If you have very high intensity interactions, then the time of the processes is very short. So let me give you connection, similar to what we have here for distance. One GeV corresponds to 0.66 10 to the minus 24 seconds. So sometimes we are measuring these the rates of the processes in the energy units. So for instance, if you have rate of the processes, which is say 1 GeV, that would correspond the time of the process 10 to the minus 24 seconds. So a very brief table, just to give some ideas which times we are talking about. So particle and lifetime in seconds. So most of the particles which we'll discuss are decaying particles. They are unstable. Only a few particles are stable. And actually, it should be some specific or some special reason why particle is stable. The shortest lifetimes are for W and Z bosons. So these are heavy particles which mediate weak interactions. And the lifetime is around 3 10 to the minus 25 seconds. Now, top quark, this is the heaviest quark we know, is 2 10 to the minus 25 seconds. Higgs boson, as I mentioned already, it's 1.6 10 to the minus 22 seconds. Now, pi zero, this neutral pion with a mass 140 MeVs, it has lifetime 8.4 10 to the minus 17. And so let's continue the table here. Tau lepton, which is the heaviest lepton, it is analogy of electron and muon, but it has mass 1.8 GeVs approximately. So it has lifetime 2.9 10 to the minus 13 centimeters. Charged pions have much longer lifetime than neutral one. It's something like 2.6 10 to the minus 8. Now muon, which is another analogy of electron, but much more massive, has lifetime 2.2 10 to the minus 6 seconds. Now, what is lifetime of the universe? Is 4 10 to the 17 centimeters. Sorry, seconds. 4 10 to the 17 seconds. One of the longest nuclei which we have observed in decay, and it has double beta decay, I will discuss this later, is xenon 130. And it has lifetime 2.1 10 to the 21 years. Much longer than the lifetime of the universe. And then we have just lower bounds on particles like electron or proton. So for electron, the lifetime for electron, if it is unstable, its lifetime should be bigger than 4.3 10 to the 23 years. And for proton, the bound is 2.34 years. So which is 3 10 to the 41 seconds. So can you tell me how come that we put so strong bound on the lifetime of proton, which is much longer than the lifetime of the universe?
You mean experimentally, or?
This is experimental bound, so everything is experimental. So we put this a lower bound on the lifetime. Maybe proton is completely stable, but still you see. So we put this bound on the lifetime of the proton, and the question is that it is many orders of magnitude bigger than the lifetime of the universe, starting from Big Bang. So this is 10 to the 17, 4 10 to the 17. How we can get this bound? Right, so just we can collect bigger of number of protons, and therefore there's small chance that one of them decays. So this is how we are getting these stringent bounds. Yeah.
What kind of decay is expected for the electron?
Oh, so for electron, for instance, it can decay into, and people are looking for this decay, into neutrino and photon. Of course, for this you need to have charge non-conservation, electric charge non-conservation. And this is actually the way how people are establishing bound on conservation of of electric charge. For proton, possible decay mode is, as for instance, pi is pi 0 and positron. This is one of the modes which is very very efficient. So let me make probably final comment. Knowledge of masses is actually contains a lot of important masses, the values of masses, contains a lot of information. And we will discuss this at length. The particle can decay into only lightest particles, at least in vacuum. So if you have a particle X, then it can decay in the particles with masses which are smaller than the mass of X, or the sum of the masses should be smaller than the mass of particle X. And actually, if you find some lighter particles than X, then decay should proceed unless there is a very good reason that this decay doesn't occur. And one example is here. So we haven't observed decay of electron into neutrino and gammas, although neutrino and gamma masses are much smaller than the mass of the electron. So kinematically, this decay is possible. However, it doesn't occur, and the reason is electric charge conservation of this U1 symmetry, which is responsible, which is gauge symmetry. Now, it can be that neutrino decay into two gammas, for instance. Again, kinematically, this is possible. However, this doesn't occur because of angular momentum conservation. So neutrino has spin 1/2, and it cannot decay into gammas which have spin 1. Now, pi is a strongly interacting particle. And in principle, there's a number of different particles to which pi can decay. However, its decay rate is very slow. Remember, it was 10 to the minus 8 seconds. It's slow because fast decays at 10 to the minus 25. These are 24, 10 to the minus 20 seconds. These are decays due to strong interaction. Here, decay is much, much slower. And this is because pi is the lightest strongly interacting particle. And therefore, it can decay only on particles which have no strong interactions. And this is the reason why pi has a long lifetime. Probably I will stop here this part and tell me if you have questions.
In the case of the proton decaying, you will violate the baryon number conservation.
Yes, so this will be with violation of baryon number.
And also it needs, I think it needs for conservation of lepton number.
Well, lepton number is also, of course, violated. Lepton number is violated. B minus L is conserved by both B and L numbers are violated. So we will discuss this in the third part of the course, and we will discuss some symmetries and how we check if symmetry is exact or not. Okay? So we start the first part of the course. That was kind of introduction, and we will repeat many things which I just shortly mentioned in this introduction. So now the first part is what I was calling leptons and hadrons. Well, actually, the name of hadron has been given much, much later. It's kind of a Greek heavy. And this was named for particles which have strong interactions, although the strong interactions have been discussed, and particles which have strong interactions have been discovered much before this name was given. So what I will discuss here, as I mentioned already, are detection of particles and principles and main notions and concepts. Remember, we define particle as point-like object, which is described, each motion is described by quantum mechanics or quantum field theory, which has a number of characteristics: mass, spin, parity, and charges, different charges, gamma, 2CD, isospin, baryon, lepton number violation. So what I want you to understand, and you need to know this, how we got this information, how we obtained this information, and why we are using these characteristics for elementary particles. Okay, so that's the goal. And of course, all this information is obtained from the experiment, so you need at least to have some kind of basic knowledge of how we got this information about elementary particles, and why this provides a complete description of elementary particles. Okay? So how we got information, its charges, and if it is complete or not. We do not see elementary particles, right, by eyes. So what we detect, kind of secondary effects which are produced by the particles. It's something like, imagine the sea, and something is moving underwater. You do not see this object, however, you're observing waves on the surface. And then, studying these waves, you are guessing what is actually moving underwater. This is something like that. So this is indirect study. And nevertheless, we know a lot of elementary particles. And why we think that this is complete description? Because knowing this, we can predict what is behavior of a given particle, how it moves, and how it will interact. And again, how it produces observable effects. So in this sense, the description is complete. Not only this, we can manipulate by particles, although we do not see them, but we, for instance, can impose electric field or magnetic field, create, and see how the particle reacts on those fields, how it moves, how it interacts, and that gives us knowledge about parameters of the particles. Okay, so I will discuss not all the discoveries, of course, but I have selected some which I think are the most important and actually gives the idea how other things have been discovered. Okay, and what I will start with the very first discovery, discovery of electron. Just remind you, I hope you so remember how it was discovered. But I want to make important conclusions. So first describe how electron has been discovered, and then we will kind of learn something important from this discovery. So electron has been discovered by G. Thomson. In 1897, so he was working in Cambridge in Cavendish laboratory. And so what he has studied? He has studied discharges in rarefied gases. Schematically, his detector was, his experimental setup was the following. So, it has cathode, then which is negatively charged, and anode, which is positively charged, and there is some gap. And what has been observed even before Thomson, that if you have high enough tension, that some rays are emitted from cathode. And what he discussed, what he actually studied, these cathode rays. So there are some rays, and then what he applied electric tension. So he has a battery for the field here, and then he studied how this electric field influences cathode rays. Okay. So he put screen made out of zinc sulfide, and actually that material has been used in many experiments. So all this has been found, empirically. So people see that if you put this material, then you will see that these cathode rays induce here some flashes of light. So what he has seen is on the screen are shining spots produced by these cathode rays. So he saw the glows of shining spots. So these are the observations. Let me now summarize. So he has this experimental setup, and everything was in the tube, like something like that. Even be precise, something like that. Here is also inside the tube with very small pressure, so it was evacuated, well evacuated. What are observations? So he saw these rays, cathode rays, which produce glow on the screen. So what he did, what are measurements? He studied deviation of spot from this straight one as a function of electric field. Right? So when he applied electric field, then the spot moved, and what he measured, this distance, as the function of strength of electric field. I'm giving this kind of detailed stuff just to then explain that future experiments have kind of all the same items. So you have some setup, then there are some observations, then you manipulate with your object which you are studying and see what is the reaction, what is the outcome. So he changed the electric field, he changed the strength of battery, and he observed that the spot was moving as a function of strength of the electric field. So, simple, right? Now, what is interpretation? Well, actually, interpretation was even proposed even before Thomson. And it was actually proposed that probably these cathode rays are fluxes of particles. Emitted from cathode. So these particles have certain mass, particles with mass, and electric charge. Then, of course, if you apply to these particles electric field, in electric field, due to this charge, it will be force which induce this deviation of shift of these rates. So this, what is called deflection, right? Thomson has studied deflection of cathode rays in the electric field. And now once we have this interpretation, we can proceed with theory. So the theory is very simple, right? So if you have such a particles moving in electric field, then there is a force which is given by E, electric charge, multiplied by the strength of the force. So this is the theory. Okay? So let us compute what is this deflection T here. Deflection is given by acceleration T, which is time of propagation over 2. Right? What's interesting, I'm using just completely classical picture here. And so although this is quantum object, in this respect, it just shows up as a classical object. Now, that is proportional to A, then L squared, the distance in which this electric field acts, over 2 is proportional. So what is important, that D is proportional to acceleration. Acceleration is given force over the mass, and therefore this deflection or deviation from horizontal direction is given by it is proportional to E over the mass multiplied by the strength. Okay, so this is acceleration. So D is proportional to acceleration. Acceleration is given by the force over m, and then I substitute the force here, and I'm getting this expression. So indeed what I'm getting here is that deflection is proportional to the strength of electric field linearly, and this is what he has observed. And it also proportional to ratio of E over m. So in this experiment he cannot measure independently electric charge and mass of the electron, but he measured this ratio. That was the outcome of the experiment. Later, Millikan has measured electric charge independently. What Millikan has studied is motion of droplets of oil in the electric field, and what he has found is that the charge, so the kind of the character of motion, is given by something which is integer of some small quantity. And this integer was identified as the smallest electric charge, and it was assumed that this is electric charge of a electron, for instance. Of course, so what he did is droplets of oil irradiated by gammas, and so they got charged, but the charge was not just 1 unit. In some cases, maybe 1 unit, some 10, maybe some more. But what he has seen that the motion would correspond to charge which is integer of some small quantity. So this is the story, right? So eventually we have found what is independently electric charge and therefore the mass. Now let me kind of extract the lesson. So what is this? Questions? Again, I just remind you. I assume that you know this. The lesson is the following. The first, that we observe effect of particle by eyes. So Thomson just saw these spots, all right? Although that is produced by elementary particle body observed by eye. Why it is possible? Which is kind of non-trivial if you start to think. This is because we had a big flux of this particle. It's not just single particle, but it was flux of particles. Each of these particles has the same behavior. So they were deflected in the same way. It is not like different electrons will, spread, they had some different effects. All these particles had the same kind of trajectory. And this is why everybody is just hitting essentially the same spot, and one can see big effect of this spot by eye. So, the flux produce macroscopic effects, which can be seen by eye. Of course, if you have very high energy particles, you can observe the particles, just the effect of the single particle. This is how Rutherford actually later saw this kind of flashes produced by a single alpha particle. But alpha particle is much, much heavier, so it produces much stronger effect. The highest energy cosmic rays have so huge energy that they can produce really enormous effects. So the energy is so big that it's equal to energy needed to take 1 kilogram of some material and put it 1 meter heavy. So can you imagine that a single particle contains so big energy? But here the energies were small, and the observable effect is because it was big flux of these electrons. The second important stuff is essentially it was a classical effect. Although this is quantum object, but it has behavior as classical particle, right? Then where quantum mechanics appears, when we have a classical manifestation of quantum mechanics. So if we have individual electron, then we don't know precisely, for instance, when this electron was emitted. So we can compute probability. So if electron is produced in some decay, or and also when electron interacts, we cannot say that this given electron will interact in this point 100%. Again, there's a probability. However, if you have flux and you integrate over the flux, these are conditions when you have the system of quantum particles which actually show up as just classically. Okay? So we are using very often this to study the properties of these quantum objects. So here we have measured electron, electric charge and the mass of the particle. Right? So we measured parameters of quantum object using classical propagation properties of flux. So, and in this case, quantum features do not show up. The third important thing is that in this setup we actually use different phenomena. For instance, how this glow appears. So when electron hits the screen, it produces this shining. By that time, people didn't know why it is produced. And it was kind of used like empirical, so they knew. So we may not know precisely what is the mechanism of production of these electrons. We don't know what is the mechanism of production of this glow. Nevertheless, we can learn something from this experiment, right? So even not knowing completely everything, we still get information. So it's not like, oh, we don't know how this spot is produced. Later, of course, we kind of understood this, and the theory was created, how this interaction of electrons with material produces these spots, and why it is this material which is the most efficient. Actually, not all the materials can be used in this kind of experiment, but this material is really very, very kind of useful in this respect. Okay. Now let me discuss discovery of proton and neutron, which are other very important particles, of course. But before discovery of proton, let me tell you about the Rutherford experiment and discovery of nuclei. And this is because this story is very important even for future experiments. So let me discuss nuclei discovery. So that has been done by Rutherford. In 1910. And what he did, he studied scattering of alpha particles on atoms of gold. The setup was the following. As in many experiments of that time, people used polonium as the source of alpha particles. Remember that time people discussed alpha, beta, and gamma radiation. And polonium produced these alpha particles. Alpha radiation. Then he put plate of gold and then he observed the scattering of alpha particles. In gold. So what he did, he put the screen again made of this tungsten sulfide. You see, in all these experiments, people use quite very similar materials. And what he saw flashes on this material produced by individual alpha particles here. Again, glow. But now it's individual particles, so he sees the flash and he can measure what is the deviation of particles. So what is the scattering angle? So what is the main result? So in our modern terms, we say that Rutherford measured angular distribution of scattered alpha particles, right? So the main result that he observed many events with scattering on very big angle. This scattering angle was of the order 1. Can be 60 degrees, 30 degrees, 20 degrees. From this observation, he made the conclusion that within atoms, the charge, the positive charge, is concentrated in very small volume, which is much smaller than the size of the atom. Okay, so that was the conclusion. And now let me give some kind of simple theory for this, because it is really important for various things. So although scattering occurred on atoms, but let me neglect electrons. I just see that I have some charge, a positively charged sphere, and discuss how scattering occurs on positively charged sphere. That would be important if we discuss, okay, so I will comment on this later. This large angle means that delta P, or change of the momentum of the particle over the momentum of alpha particle, is of the order 1. Or the scattering delta P change of the momentum is comparable with momentum itself. So what we have here, alpha particle in the initial state, then it is P prime alpha scattered. This is theta, and so this is delta P. So now let us consider scattering on charged sphere. That time people thought that maybe we have atoms, and the model was like you have atoms and electrons, and actually nuclei is of the size of the atom itself, so which means that electrons are moving in this in the field, positively charged field inside the atom. So if we have such a sphere, well, let me put it a little bit lower. And consider scattering, and let us introduce impact parameter, RH, and let us introduce the size of this sphere as RB. And if we have scattering with impact parameter, which is much bigger than the radius of this sphere, then it will be quite weak deviation. Like this. So if the impact parameter even bigger, then it will be just very small effect, because particle will spend too little time in the place where the strong electric field. So for this particle, the electric field is always very small, so we'll have like that. Okay. So what is delta P in this case when you have a big impact parameter? In this case, delta P is proportional to charge over the impact parameter. So this is the momentum change in the case where impact parameter is much bigger than the radius of the sphere. So that can be actually computed. Since you know what is electric field, you know that the strength is 1 over r squared, and you can integrate over trajectory and you can get this change of the delta P. This can be obtained also on dimensional ground. So parameters in game are electric charge and impact parameter. There is no more parameters in this problem, and therefore just on dimensional ground you can say that this delta P should be somehow inversely proportional to the radius, which has physical meaning, right? So you can do this when you integrate the force. So the force is 1 over r squared, and then you do integration, and then eventually you will get this 1 over r in the first power. Agree? So now let us consider the situation when impact parameter is smaller than the size of the object, and this impact parameter close to the object itself, so we have propagation of this type. And of course, you see, the smaller r, the closer trajectory to our charged body, and therefore the stronger effect. So this is reflected by 1 over RH, right? So the smaller RH, the closer to our particle to this charged sphere, the stronger electric field is, and so you have stronger deviation. So now let us consider the situation when impact parameter is smaller than RB. So in this case, not all the charge of this sphere will produce the scattering, but only the part of this charge. Probably you know that if there's a low 1 over r squared, then what happens when your particle is sitting here, that effect of these external layers cancel each other, and the only what produces effect is something, the charge which is within this sphere. Okay, this is consequence of 1 over r squared forces. So, if you have impact parameter smaller than RB, then the charge will decrease. So how charge will decrease in this case, which produces the scattering? In this case, the charge will be given by total charge multiplied by R parameter over B in Q. So just computed the volume of this, and I assume that distribution of the charge is uniform. Then I get this answer, right? So the charge which will act on our particle will be reduced by RH over RB in the third power. So in this case, delta P, change of the momentum, which will be given by, so let me put also here H, will be given by QH over H, and I insert here this expression, what I will get, Q total, multiplied by RH squared over RB cube. Okay. So I just inserted here this expression, and I'm getting this 1 power here cancels, and I get R squared. Okay. Now I can draw dependence of delta P on impact parameter. So here important scale is the size of our sphere. And at big impact parameters, I have this 1 over RH dependence. I will have something like that. And at low energies, I will have increase like RH cube. So somewhat, it will be like that. So here it will be 1 over RH. Here it will be RH squared. Sorry, not cube, squared. So the biggest delta P corresponds to impact parameter which coincides with RB approximately, right? So in this way we can measure RB if we know how this delta P became. Now let's come back to Rutherford experiment. And if you assume that this sphere with charge has the size of the atom, which means 10 to the minus 8 centimeters, this is the size of the atom, then you will get, according to our formula, that maximal transfer momentum, so maximal change of the momentum should be Q over RB, right? So the maximum is here. And you will find that this is something like 10 to the minus 6 GeVs. So if electric charge is distributed uniformly in the sphere of the radius of atom, then you would expect that the maximal change of momentum at the scattering is 10 to the minus 6 GeVs. So actually it should be even smaller. Put here even smaller, it should be smaller than this. So this you will get if you are sitting in the pit. So if electric charge, if you have nuclei which is of the size of the atom, then you would not see, you should not see a very big change of the momentum. It should be 10 to the minus 6. Now what Rutherford has the following. It was known what is the velocity of particles, alpha particles, which are emitted from polonium. So you can use, for instance, electric field or magnetic field to measure what is the momentum of the particles. And it is known that P alpha in Rutherford experiment or emitted from polonium is something like 0.1 GeV. So it is known that the momentum of alpha particle emitted from polonium is 0.1 GeV. As you remember, what Rutherford has observed is that delta P is of the order P. And the angles are big, so he observed a number of events with this big delta P, so that should be 0.1 GeV, which is 5 orders of magnitude bigger than what would be expected if you have nuclei of the size of the atom. Okay? I'm doing this very slowly and just to understand this has a very general feature. So you will meet this many times in future. Also when we will discuss the transition from hadrons to quarks, to the quark level. So it's 5 orders of magnitude difference, which means that the size of this sphere should be 5 orders of magnitude smaller than this 10 to the minus 8, the size of the atom. And so we can immediately find that the size of the nuclei should be 10 to the minus 13 centimeters, 5 orders of magnitude smaller. So the size of the nuclei is 1 over this delta P. And that will be 10 to the minus delta P is 10 to the minus 13 centimeters. And this precisely gives you the size of the nuclei. So in this way, we measure what is the size of the nuclei. So generalizing, using the scattering and measuring angular distribution and finding what is the maximal momentum change, you can find out what is the size of the object on which scattering occurs. And now we can come back to our first discussion about the size of the quarks, or size or point-like character of quarks. The story is the same. So we perform scattering, and what we have found that actually the scattering effect corresponds to point-like, that the charge which actually produces the scattering is, if finite size exists, the size should be smaller than 1 over these 6 TeVs, and we get in this way the size, possible size of the quarks. The size should be even smaller than this, because we haven't found any deviation. So here we are saying we have hard collisions, because if the charge is distributed uniformly, there is no big deviation, and we are talking about soft collisions, because it's kind of not a big deviation. The system doesn't produce very strong deviation, change of the momentum of scattered particle. What has been observed is hard collision. Because of the smallness, the charge is actually concentrated in very small volume, and therefore you can get, in some cases, scattering of big angles. So I will use this example many times in my course without repeating all these arguments. Okay? So this is discovery of nuclei, or discovery of the size of the nuclei, so to say. And now let us jump to the proton. And the proton discovery or introduction of proton has a long story. So the proton is just nuclei of hydrogen, right? So the proton as a constituent of nuclei has been actually proposed by Wien in 1898, 1 year later after Thomson's discovery of electron. Actually, what he suggested that actually protons or nuclei of hydrogen are the parts of all the nuclei. So that's kind of elementary objects in nuclei. What is considered as discovery of proton is a discovery by, again, Rutherford of nuclear process when alpha particle scattered on nitrogen led to emission of hydrogen plus oxygen 17. So that showed that protons are really contained in this nuclei. So this appearance of hydrogen nuclei in such a process is considered as discovery of proton and confirmation that protons are constituents of the nuclei. Okay? So let me say a few words about discovery of photon. Again, I just very briefly remind you what are main points here. So you know that the photons or light as the flux of particles has been discussed since ancient times, since Greek time, long time ago. And that was renewed, this idea, by Planck and Einstein in the beginning of last century. And what Planck has suggested and he was trying to create a theory of black body radiation. What he actually proposed that the spectrum of black body radiation can be explained if the energy is emitted in quanta. It's not just something which is kind of smooth flux, but in quanta. And each quanta has the energy h nu, and this is his famous Planck constant. It is related to the frequency of the light. And then he can explain in this way the shape of black body radiation. What Einstein said in 1905 is actually not only the energy is discretized, but the light itself is a flux of the particles. And of course, in this way, you immediately get that the energy is discretized. So what he was saying that the radiation, not only radiation, but what we have is actually a flux of the particles. With mass 0, with energy given by frequency, as Planck also suggested, and momentum as or h nu over c. So, and these particles are moving with velocity of light. So this is speed of these particles. So they are massless, and therefore they are moving with this speed. Now, what is the confirmation of this idea? Tell me what you know. Just
Compton.
right? And before that, yeah. So the spot effect, which is discovered by Millikan, and actually confirms the picture that if you have photons hitting the surface, then you may have appearance of electrons produced by these photons. There was also X-ray scattering experiment by Hobby, but final confirmation came from Compton experiment, as you said correctly. Now let me remind you what is this. Check. What he has studied scattering of X-rays on electrons. So suppose we have really light as a flux of the particles. So we have gamma, and here is photon, and this is photon in final state. Here is electron, and this is scattering angle. You see, many of these early discoveries have been done by just studying kinematics. So simple kinematics, like in Thomson experiment or Rutherford experiments, or just simple kinematics, essentially classical picture. No need to have quantum mechanics here, right? So what's going here? What has been measured? What has been measured is the frequency of scattered light. So we have here frequency nu, and here nu prime. And what has been studied is how frequency of scattered light depends on scattering angle. So this is the experiment. Dependence of scattered frequency on theta. So, if you have this interpretation of light as a flux of the particles with those characteristics, you can just consider simple kinematics of this process and find out this dependence. So, we have here gamma plus electron, go to gamma prime plus electron, scattering, and we know that we have an initial state, the particle, with energy h nu, with momentum h nu over c, and in final state we have E prime with h nu prime and P prime equals h nu prime c. Then you just apply energy momentum conservation for this process. And I don't want to do this on the blackboard. This is a simple exercise. Using this kind of interpretation, you can get dependence of eta prime or eta prime on theta. So once you know this interpretation as particles, and you know what are the energies and momentum of these particles and the mass, you just put energy momentum conservation for this process, and you find what should be dependence of P or energy in final state, and therefore the frequency. And so Compton has found that it's in very good agreement with observation. So that was a final point of discovery of photon. And so photon as elementary particle. Okay? Next discovery is discovery of neutron. Who knows how neutron was discovered? So what is the story with neutron?
I think it was Cavendish or something like that. They discovered.
Well, Chadwick, yeah. So, neutron in all these cases there's some prehistory of discovery. It's not just it's very rare cases when someone is doing something from scratch, so nothing was known before, and just doing something absolutely new and opening something new. So usually there's some prehistory. And the story is the following. In 1930, Botte and Becker observed that when alpha particles hit beryllium target, they produce some new radiation. Again, they use polonium as the source of alpha particles. Then they use beryllium target. Actually, they used also boron and lithium. So there were different, but beryllium was the most efficient producing this radiation. So they produced something. So here's alpha particle, which has no electric charge, but that's clear. It's easy to check. So I have the reaction alpha plus beryllium and plus something. And then you can ask how he knows that something is produced, because then he put paraffin, which contains protons, and then he observed that that actually this radiation knock protons from this paraffin, which means that there is some object which has the energy, momentum, and interacts and can knock out protons from the material. The question was, and that was lucky time because number of known particles was too little, and the question was, is this, put here, okay, maybe I immediately put this n, so let me put n as a neutron. Is n just photon? So the first blame is maybe it's just photon. And whole discovery was to establish that this radiation is not photons. And then he got Nobel Prize, Chadwick, for this. It's a simple thing. We established that this is not proton. Again, kinematic was used. And again, it was not immediate step, but that was also another experiment by Joliot Curie and Joliot. Which actually measured the protons. So this experiment of this type, but then they put also paraffin, like also Botte and Becker. And they measured what is the energy or momentum of protons, which actually knocked out of paraffin. So this layer of paraffin, protons appear here, and they measured what is the energy of the proton, momentum. So what they have found that kinetic energy or momentum, let me put it this way, is something like 5 MeVs. If this is N is gamma, then one would expect something like 50 MeVs, again using usual kinematics. So what they have found that the energy of proton, which appears after interactions with this of this particle, is much smaller than what is expected if this particle is gamma. And actually, Majorana, when he heard about this, he immediately concluded, oh, this is not photon, certainly then that should be new particle. I don't know if he published something or not. So then, how to check this? And what Chadwick did, he checked, actually, again using kinematics, if this new particle is proton or not, or photon or not. So what is Chadwick experiment? Essentially, very similar. Polonium emitting alpha particles, knocking beryllium target. So here, this new radiation appears, again paraffin, which actually leads to production of protons here. And what he did, he measured angular distribution of this emitted proton. So he used ionization chamber, and so what happens is protons enter ionization chamber, ionize, and produce current here. And so he measured current, and then he moved these things, and saw how the current changed when he moves. Again, the same story, you see. It's measurements of angular distribution of scattered protons, or protons which appear. And then you just do kinematics. So you have this N plus proton, and you have P prime, so proton which is scattered. And then, depending on the mass of these particles, you would have different angular distribution of protons which appear. So imagine that you have very light particle. Suppose the mass of N is very light. Then it will not produce scattering on big angles. Right? So just using kinematics, one can find what is the mass of this particle. So it's kinematics. Again, energy momentum conservation. So it's again this particle N. And then he can find what is the mass of N, and he has found that, in fact, the mass of this new particle is something like 900, around, say, 0.1 GeV, let me put it, 0.9 GeV, 0.9 GeV. From kinematics, from angular distribution of scattering of this new particle onto protons, he concluded that the mass is much heavier than, and of course, it's massive particle, it's much heavier. The mass is close to the mass of the proton. Angular distribution of these protons corresponds to the mass of the particle, which is approximately mass of the proton, much heavier, so it's heavy particle. It's approximately 0.9 GeV, which is quite close to what we know now. So So that was the discovery of neutron, and Chadwick got a Nobel Prize for this experiment. Also, you see there were some measurements even before, and already people before did conclusions that this particle differs from photons. So the conclusion was that n is not gamma, and so this new particle. Questions?
At this time, at 1930, they had...
That was 1932, by the way. So that experiment was by Chadwick in 1932.
So protons had already been discovered, and they know...
Yeah, Compton, yeah.
Yeah, they know about the charge and the mass of the proton.
Yeah.
So they can, for example, calculate ratio of E, the charge over the mass for alpha particles, which actually the nucleus of the helium. So maybe this can tell them something about that there is extra neutrons, extra new particles.
Yeah, that's a little bit not as simple story as this one, because people thought that maybe electrons still inside. So you have helium, and you have helium which is 4 protons and 2 electrons inside.
But this can't be because they know that the alpha particle is positively charged.
So yeah, the charge is 2. So you have 2 protons, so 4 protons and 2 electrons inside. There's no neutrons.
Yes, okay.
So we will discuss the discovery of neutrino next lecture, and you will see people were struggling to, because it was not like a transformation of particles. People still saw that if something is emitted, it's still contained inside the nuclei. And then the question was how neutrinos are sitting inside. So electrons, okay, beta decay, because you have electrons already sitting inside the nuclei.
Did you say that the alpha particle is with 4 protons?
Yeah, so it was idea. When it was discovered, when people used this, yeah?
I think it's 2 protons, I mean it's helium, right? So it's 2 protons and 2 neutrons.
Yeah, after.
Before they thought that, or?
Before, so after discovery of neutron, people start to, to produce the theory which we know now.
Okay, I see.
Not only this, what I'm saying, so that helium-4 was considered the system of 4 protons and 2 electrons.
I see.
So you have charge, you have correct mass, and all other nuclei were considered also composed of protons and electrons, and therefore you have beta decay of nuclei because one of these electrons just going out.
There should have been more experiments in between to determine that neutron is not charged.
Yeah, so they use electric field and magnetic field, and so that it. Of course, you always put some upper bound on that, but that was checked. Yeah, so there's no deviation. These fields go. Well, magnetic field actually affects, but not very strong, because neutron has magnetic moment that was established later, so it interacts with this magnetic field.
How did I find that the proton and electrons have the same charge?
The proton and
Electron.
well, you see, they measured the charge of the electron, right, after Millikan experiment, and probably there were some other measurements, and then they know neutrality of atoms. But of course, you can measure also the charge of the proton by, say, forming scattering and magnetic field. But the most strong boundary just comes from neutrality of atoms, so which means that you need to match the charges of proton and electron. Neutrality of atoms, yeah.
And how do you know what Majorana said if he never published?
Sorry?
How do you know what Majorana said if he never published it?
Well, he probably gave the talk. I knew this from the books. Not my runner, but other people. Okay.
Do we have tutorials next week or?
Sorry?
Do we have tutorials?
So what I will do, most probably, because I'm giving tutorials related to my lectures, probably not, but after that every Wednesday you will get tutorial. So most probably I will give you the exercise by the end of this week. I haven't yet decided.
It's postdoc eating them or?
Yeah, I need still to find.
Okay.
Did you stop the recording?